thank you for coming here early in the morning. I'm not so early, but yeah, thank you anyway. And this is a joint event held by my team, continuous optimization team, and also MIHO's team, functional analytic learning team. So this is a joint event. And thank you for coming here. And okay, so let me introduce AIP Center first. And so so you are now here. And DCAM was founded in 2016 by the support of MEXT. And this is the anniversary year, 10th year. That's why we have this kind of workshop. And so now AIP consists of these members. And I'm here, and also MIHO group here. So we are belonging to generic technology. We are working on some theoretical work of written in this area, statistics, optimization theory, something like this. So this is the group members, team leaders, I should say team directors of AIP Center. And so as I mentioned, this is 10th anniversary year, and also this is a final year of support of MEXT budget. Of course, we'll continue. So this is not the end of this center, but still, this is the 10th anniversary year. So that's why AIP Symposium is planned at the end of this fiscal year. So we are now here. So if you are interested in other research groups report, please join other workshops too. So we are now here. So I said that 10th anniversary year, and MEXT support was over, but we are moving on using another budget. So we are now in this category, and we will continue. So yeah, work together from now. Work together from now on. Okay, and I'll summarize aim of this workshop. So we want to summarize and promote the results of project studied in our team. So thank you for coming here to listen to our research reports. So we have plenty of research results during the last 10 years. So we want to explain some of them, not all, of course, but at first I will start using 30 minutes as the introduction. And then after that, Pierre and Harold will talk. And we have a guest, Christophe. And after that, we want to learn other research area close to us. So I know that Andreas, we are working on similar things, but still you have plenty of knowledge of control and signal processing. So yeah, okay. So I'm so excited to learn something from your talk. And also Benjamin, you're working on sparse modeling in a flavor of finance and economy. So we can learn a lot. And also this MIHO's group research results, we are new to your area. So we want to learn some from your team. So I'm so excited to have you guys as a lecturer this afternoon. Okay, so this is the two main purpose to present our own research results in this morning, and then afternoon we want to learn more about your research. Okay, so let me introduce our former members. So far, these members belong to our team. So I excluded the short-term visitor or short-time researcher, but they're belonging to our team, and I worked with them on these topics. So I'm thankful for these members, and 3 members are out from Japan. So some of them are working in Italy, Canada, and Australia. And other members promoted from this team to be associate professors in other universities. And now I have current teams. So you guys are here. So they're belonging to my team currently. Okay. All right. So I want to share what we have done so far during 10 years here in AIB Research Center. Okay, so we are developing algorithms for various classes of optimization problems. And we want to do something interesting in terms of theoretically and also practically. So we try to develop new algorithms, and our purpose is to give very sophisticated algorithm that has a theoretical guarantee. So this is what we want to do. And so far we are targeting these problems, but of course we are not restricting these problems. But I'll pick up the two research topics to explain, showcase what we have done. Okay, so at first we'll start with bilevel optimization. So bilevel optimization, it is influenced by machine learning research field very much. So to be honest, bilevel optimization started since maybe before 1980s. It has a very long history, but this 35 years, maybe, publication number is something like this. But 2017, we have a very unique and interesting algorithm in machine learning area. And since then, rapidly, the publication number has increased. So last 7 years, we have already this very big number of publications compared to 35 years. So I was surprised to see the power of machine learning communities, because the number of papers drastically has increased. Okay, and so let me introduce some simple application of bilevel optimization in machine learning. So let's see. Okay, suppose that we have 20 points like this, red dot. And we want to find the best fitting curve to express this points, and then using 20th order polynomial. So W's are variables, and we want to give weights for this polynomial, and maybe this square loss function is natural to think about this application. But in most cases, we add this regularization term by fixing some hyperparameter, lambda. And lambda is very important, because if we ignore lambda, or if we set lambda to 0, maybe we can get this curve perfectly fitting. So 0 residual in terms of this top part. But let me see, it's not good in terms of prediction, of course. For example, we want to see the correlation between height and weight for each person. And this dot shows the data. And maybe for the people whose height is around here, what is his or her weight, and then maybe 0 would be the natural guess from this dot. But if we use this perfect fitting curve, then it will give us plus infinity maybe as a weight. So it's, of course, it's a very bumpy, curvy. So it's not good in terms of prediction. So if we tune lambda well, then we'll get this curve. This will be useful when we predict y-axis from x data, right? So lambda is important parameter when we use this type of prediction model in machine learning area. And how do we find best lambda? So of course we can do trial and error, but one option is to solve this type of bilevel optimization problem. So lower level problem try to solve this problem, loss function plus regularizer, by fixing lambda from the upper level problem. So upper level problem try to find the best lambda in terms of prediction. So suppose that we have a data set whose label Y is already given. So, and we can split the data set into two. One is for training, one is for validation. And this validation, this objective function is to find the best lambda hyperparameter. And lower level is to solve to find the best weight W. So this is the bi-level optimization to find the best lambda hyperparameter. So in a way, bi-level problem can play an important role in machine learning area. And yeah, of course, it's not only one application. Of course, there are plenty of applications in machine learning using bi-level optimization. But anyway, bi-level optimization is important application, and that's why the number of publications rapidly increased recently in machine learning area. Okay. And what we have done so far using in this for machine bi-level optimizations. So I categorize A and B, so depending on the approach. So this is orthodox mainstream approach until 2017. The approach is to replace this lower level problem by optimality condition, I mean KKT condition, and then use some optimization solver to solve the problem. So after replacing this part by KKT conditions, it's possible to use some software, optimization software to solve this problem. And at 2017, this idea is something like this. So this research stream assumes strongly convexity and plus in addition to differentiability to the function G. And then this is a unique solution. So you can think solution path depending on X. So if we squeeze this one into the objective function, this problem can be considered as a composite function, and the variable is only X. So we can calculate hypergradient of nabla F using a chain rule. So this approach is gradient descent method for solving bi-level optimization problem using a chain rule for the calculation of hypergradient. So very simple. And of course, a strong assumption was given because strong convexity is necessary for this part, but computationally fast compared to this one, if the given problem is simple enough like this. Okay. So what we have done so far for the research stream, we relax this part. So I said that in general, this lower level problem is replaced by a KKT condition. So for the purpose, differentiability was necessary for G. But to enlarge the application to deal with like LP norm, P is less than 1, then not necessarily be differentiable. And that's why we use smoothing technique for make this function smoothen. And lower level problem, and after that, lower level problem is replaced by the KKT. So approach is very simple, just using smoothing technique. Function is smoothened, and then KKT conditions are taken. So, but theoretically, it's difficult. What we don't know what kind of solution we will get by the approach. So we define, for the first time, we define this necessary condition, B KKT conditions for bi-level optimization problems. And then we prove that our method will converge to BKKT point. So this is our contribution. And this work was based on these collaborative works. So Harold is here. So this is part of Harold's work. Okay. Approach B, what did we do? So we try to enlarge the application of this problem. I mean that method for this problem is generalized somehow. Well, one direction is to the bi-level approach was extended to multi-level optimization problem. So bi-level is already complicated structure, but we are so brave to make it more general, not only to 3, 4, more than that. So we, but this is a kind of straightforward application. So we could use the idea of calculating hypergradient, and we just generalize the calculation of a hypergradient to complicated multi-level problems. So this is one of our contribution, and second contribution. So we so far this method did not allow to have constraints, because gradient-based method, if we assume some constraint, it becomes complicated. But we could deal with some type of constraint. I should not say constraint, but Riemannian manifold. By thinking of Riemannian manifold, we can restrict the space of the Y into some space using the Riemannian manifold. So we use a Riemannian, maybe, Riemannian grad or something. So we proposed that kind of approach in this paper. Something like this. So we allow to have this manifold here. So we use a manifold optimization technique for bi-level optimization problem. Okay. And last, I'll move to the last topics, high dimensional optimization problem. So I want to share the research results contributions for this research topics. Randomized subspace algorithms. So suppose that we have a very high dimensional problem. So I mean that this dimension n is very large and difficult, sometimes difficult to calculate a gradient or Hessian matrix or something like this, very large. And then using random projection techniques, we can project the high dimensional space into a subspace randomly. We can only calculate a gradient or Hessian in a smaller space. This is the idea used in random subspace algorithms. And of course, we want to maintain some important properties like global convergence and iteration complexity. So this is important. Is it possible to maintain those properties even though we calculate a gradient Hessian in a smaller space? So this is important research question. And then you may know that recently neural network tend to have a very large variables. Then we can solve these kind of problems by using a subspace idea. And let me introduce the idea of subspace method, but we'll start from full space optimization algorithm. You already know full space optimization algorithm well, but let's review the methods. So we are thinking of iterative algorithms, and we are now in a kth iteration, and we have xk here. And we try to find the best direction to go, such direction decay. And usually we solve this type of problem, but of course it's difficult to solve this problem exactly. So we, for example, by using Taylor expansion, first Taylor expansion, second order expansion, we approximate this function like this and get the, for this case, steepest descent direction or Newton direction can be achieved in this way. And now let's move on to random subspace algorithms. So random subspace algorithm, we use a random matrix PK. And PK, it's a fat matrix, and transposed means that tall matrix. So the size of UK decision variable size becomes S. So we assume that S is pretty much smaller than original space N. And so we try to solve this problem, but again, we'll use a first order approximation for this function F or second order approximation. And then like this, we'll get random subspace gradient descent or random subspace Newton method are achieved in this way. And here, it's easy for me to explain the benefit of thinking subspace method for second order method, because here the inverse operation is done for S by S matrix. No more N by N. It becomes S by S. So that's why it becomes a very simple, easy computation. And after getting this one, UK, we just squeeze UK into here, and then we can update a whole sequence in this way. Whole spacing update can be done in this way. And first order algorithm, of course, it's nonsense to calculate gradient and pk separately and multiply. We won't do that. We try to use some AD, automatic differentiation, for calculating this part altogether by following in this way or something like this. So this is the idea of Kozak, and it is a random subspace first order algorithm. And second order random space second order algorithm, it has there lots of recent works on it. And up to this point, 2020, mainly the methods are for convex optimization problems. But recently, the ideas are applied to non-convex optimizations around 2022. So at the same time, we proposed, we did a similar work with them, and we all together, we are working on a non-convex optimization, random subspace second order method for non-convex optimization problems. And quite recently, our paper was accepted by ICRA. The work is random subspace truss region method, and it has a very good theoretical guarantee. Okay, and now there are some random subspace method for constraint problems like this. So constraint problems becomes more challenging because we need to maintain feasible points iteratively. So this work assumed to have efficient algorithm to solve these sub-problems. But it does not necessarily have such a sophisticated algorithm to solve these sub-problems. So we propose a new random subspace algorithm that generate epsilon KKT point of in this iteration complexity with high probability. So all of this method have this kind of iterative complexity with high probability. It becomes stochastic method. So the theoretical guarantee is done in expectation way or high probability. Okay, so I showcase our recent research results here. And Pierre will talk about these topics later. So I'll stop my talk, but we are working on these topics with the help of Pierre. So et al. Pierre's name is hidden in et al., but all of them are joint work based on Pierre. Okay, and important research question is the worst case iteration complexity. So how many iterations are necessary to find a epsilon stationary point or KKT point? So this is our research question. And some works are working on local convergence rate too. Okay, and this is research results of our recent paper and random subspace truss region method. And each sub-problem becomes minimum eigenvalue problem. So the size of matrix becomes small, S by S. So it's easy to apply eigenvalue computation for this problem by using random subspace techniques. We maintain some theoretical guarantee first local convergence rate under the upbeat strong assumption though, but we can maintain some good theoretical guarantee. And you see that we have a very good, that method is also good in terms of practical purpose, it has a very good results. And this figure shows that theoretically, the second order speed is shown. So this R is corresponding to S, reduced subspace size. And this one no more satisfy our assumption. So that's why no first speed up. But at first, the assumptions are satisfied. We will see the first convergence rate locally. Okay, so I want to summarize my talk. We are developing algorithms for various types of optimization problems, and I only showcase several research results so far. We have done for 10 years. Harold and Pierre will talk about their own research results from now on. And also, I'm happy to exchange ideas with other researchers who have different backgrounds. And our research center still continue. So I want to have lots of members to work together. So thank you for coming. And also today we have a long seminar symposium. So enjoy until the rest of this workshop. Thank you. Okay, so any question, comments? Okay, thank you.
So thank you very much. So yes, today I want to be more specific about the adaptation of second-order methods, second-order and first-order method, so Subspace Newton and Quasi-Newton. And yeah, so this is based on a joint work with Terinari Fuji, Miyaishi, and Akiko Takeda. And so first I will speak a little bit more about the Subspace Newton method, and more precisely I want to focus on the issue of local convergence. And then after that, I will explain quickly the subspace quasi-Newton methods using different kind of random matrices. So yeah, so it was introduced before, so I will be quick. But here we consider the optimization problem. And so in the first topic, so Newton method, we assume f to be twice differentiable, non-convex function. And for the second topic, f is only a C1 function, so continuously differentiable. But okay, let's start with the first topics. And then, yeah, as explained before, in subspace optimization, the idea is that at each iteration, you somehow lower the dimensionality of your problem by restricting the objective function to some subspace. And what you want to do is that, because you don't know in which direction your optimal solution here, you will change your subspace at each iteration. Because of course, if you keep P, the matrix P fixed, then you will not get the optimal solution unless the direction is inside P. But you don't know the optimal solution, so you cannot fix it in advance. And yes, so the idea is that P represents the basis of the subspace. So for example, if you are familiar with coordinate descent, so in this case, P is just some column of a permutation matrix. So you just choose some basis, so some columns of the usual basis. So just took some random permutations, select S of them, and this is what's inside P. But the idea is that you can choose a random basis. So you choose P randomly, so give you a random basis, and then you have stronger guarantee in this case. So that's why we choose a random matrix. And yeah, so the idea in this, when you use subspace methods, you want to show that can we speed up the computational time, and what about the global and local convergence property? And yeah, so this is the first work that considers the random subspace Newton methods. So just to explain quickly, what you do is that, so because you at each iteration you consider this function, so then the Hessian of this function is here. So just you project the Hessian with P on the both sides. And then you have the small gradient here, so the gradient multiplied by P, so the subspace gradient. And then so you do the usual Newton space on the small space, and then using here, this matrix PK transpose, you bring back everything to the full space. And yes, so there has been a lot of work about the subspace Newton, so convex and recently non-convex. But for me, there is something lacking in all this work, and this is local convergence. Because for me, the most important thing when you, I mean, this is just my view, but when you use this second order method, I think the most important thing is to study local convergence. And up to now, of course, there was some local convergence property studies in some of these works, but they only show linear convergence, linear local convergence. But then there is no point. If you have only linear local convergence, then you can use gradient descent. You will get the same result. So for me, the main interest was with these Newton methods in the convex or non-convex case, can we get superlinear convergence? So this is for me the main interest, and up to now, no one has studied this problem. So I think it's very interesting. Yes. So as I said, so here we consider a general setting where the function can be non-convex, and if you want the Newton direction to be descent, so when you consider this direction here, so remember, so the small Hessian multiplied by the small gradient, if this matrix is non-positive definite, so this, in general, this is not a descent direction. So this is why you need to add something called a regularizer. So you add some term here to make sure that this is a descent direction. So if you are not familiar, what you need is that the smallest eigenvalue of this matrix is positive. So this is what we do. So we use a technique in some, I think there's recently a lot of research focusing on how to choose this regularizer. But especially in the last few years, a lot of people, I think, are studying what is the best choice for this. But due to its simplicity and its ease to use, so we use some, I don't know if I cited it. Yeah, so we use this paper. It's quite old, but I think the results are quite strong because the algorithm is very simple. There is no complicated subroutine and things to use, so it's very simple, and they show something very strong. So even if the function is non-convex, they show that under some mild assumption locally, then you can get superlinear convergence. So this was, I think, this was the right choice to use this paper for the regularizer. And so, yeah, how do you choose it? I think it's in the next slide. Yeah. So this is not important, but just the regularizer. So here we have the subspace Hessian, and then we add some multiple of the smallest eigenvalue. So if the smallest eigenvalue is negative, then this is 0. But if this is if the smallest eigenvalue is positive, then this is 0. Otherwise, we add multiply by -1, and so this becomes strictly positive. And then we add some term that is proportional to some root of the gradient. And then what we do, we have this search direction. So this is the small Hessian. This is the small regularized Hessian, and we use some classical backtracking line search. But yeah, this looks complicated, but it's just what I said before. So, and just here you have the definition of the regularizer. And yes, so again, I want to insist on several things before. Excuse me. So I come back here. So the idea that there was two questions. So can we speed up computational time? So the answer is yes, because locally you see that this computation is easy to do. We can compute the full matrix and take its inverse, or we can use some more sophisticated technique like using iterative algorithm to compute this, use Hessian vector multiplication. So I will speak a little bit about this in the computation experiment, but clearly locally we can speed up, we can save some computational time. And then globally, I will say later, but yeah, at every iteration, we can save some considerable amount of computational time. Okay, so I will be very quick on global convergence because of the lack of time. So yeah, the assumption is that the sublevel sets are compact, and we assume that the Hessian is Lipschitz. And then you don't need to worry about all the constants, but what is important is that we have almost sure convergence to a stationary point with these methods. So you can see that actually the probability that we converge increase to 1 with the number of iteration. And yeah, what is important is that we have this extra n over s factor that appear. So if you use the classical Newton method globally, so you will get the the same rate, except that there is not these factors that appear, and of course there is no probability. But yeah, at the end because we have almost sure convergence, so we don't have to. The good thing is that we don't have to worry about the size S is. It can be anything. It can even be constant, and it will converge globally to a first order stationary point. Then, okay, I want to focus about this local convergence issue. So here we assume that we are close to some optima. So in optimization, with this second order method, you want to see when you are close to some local minima, what happened? Can you speed up the rate of the algorithm? So this is what we mean by local convergence. And usually with a second order method, Newton, then you can expect some quadratic acceleration. So when you are close to your local minima, you will speed up a lot. And as we will see in the experiment, so first it decreases slowly, and then at some point the function decreases really quickly to the optimal value. And so we want to study these things. So yeah, so there is three things actually I want to show. So first, that we can always have this local linear convergence to fx bar. And then the second is that if f is strongly convex, then unfortunately we cannot get this we cannot get this acceleration. But however, I didn't write it, but at the end I will show that in some case, so when the function has low rank, and this is especially relevant in machine learning problem, then we can actually obtain this superlinear convergence. And we will see all the plot, and I will explain how it works. So yeah, so you can say why do we need to use random matrix here? Maybe we can just pick some matrix with some good direction, so use the previous gradient or something like this, and it's good enough. But actually, for our proposition to work, we need the randomness of the matrix. One thing that is important is that this random Gaussian matrix P. So when you consider the small matrix, so P times P transpose, it's a small S by S matrix. So then this is close to the identity. So basically, it means that another way of saying it is that the non-zero singular value of these matrices. So this is the S by N matrices. So there is exactly S non-zero eigenvalue, singular value is probability 1, and N minus S will be 0. But the non-zero singular values, they are almost all the same. So this is what this result says. And this is important somehow in our proof. But yeah, this is not, of course, this is not all. So this is a well-known result in random matrix theory. But yeah, we need to use these kind of things in our paper. And so for the local convergence assumption, so yeah, we need two assumptions. So we need this, the Hessian is Lipschitz, and also we need to consider the subspace size large enough. But actually, this is a bit too strong. So we can assume that S is much smaller than N, but actually it can work also if you assume that S is smaller than some constant time N. So yeah, just as we don't want that the subspace dimension is too close to the original dimension. So this is some assumption, but this is very natural because we want to, if S is close to N, then there is no point in using this kind of methods. And yeah, the other assumption, some assumption we need is that we assume that the rank of the Hessian, so the rank of the Hessian at the local solution, x bar, this is greater than some constant time N. So this is some kind of, we assume that the rank is non-zero, is bounded below by some constant times the dimension. And also that for the local height, so this is something that is a little bit weaker than the usual PL condition. So maybe you are familiar, there is a lot of local conditions that are used for this local convergence rate. And more or less, they are all equivalent. So in some, if the function is smooth enough, then they're almost all equivalent. So you have Holder continuity, PL condition, and one other I forgot. But here we slightly take something, a weaker one, because usually rho, this constant rho should be between 0 and 2, and here we assume something a little bit weaker. But if you are not familiar, so you can think that somehow this is some kind of strong convexity. So somehow the function is strongly convex locally. So this is what it says. If you are not familiar, just think of this as, yeah, near the solution, the function is somehow strongly convex. And so yeah, one good thing is that even though the Hessian has low rank, then on the subspace, usually what happens is that you can show that the subspace Hessian is has a strictly positive eigenvalue. So you see that this lambda bar, what is it? It's the smallest non-zero eigenvalue of this Hessian here. But then on the subspace, if you are close enough to your local solution, you can show that there is no zero eigenvalue. And this was with high probability. And then what you can show is that this is some local PL conditions. Sorry, this here. You can bound the gap of your current iterate with the minimum value on the subspace with respect to the true gap. So this is what this theorem says. So I remember that at each iteration, you fix some subspace P. So on this subspace, you can only go up to this point. But here we want to go to this local solution, the cost of this local solution x bar. So this is some equation that link the two quantities. And using this, once you have this, it's very easy to obtain the local convergence rate. And yeah, actually, it's exactly the same as in the classical Newton. As in the what you expect. So you have the condition number here. So this is the smallest non-zero eigenvalue, and this is the maximum eigenvalue. So this is some kind of condition number. And then you have also this extra factor, so S over n, that is with respect to how big the size S here. However, I just want to add something. So this is somehow a conservative rate, but you can show in some time, even though it's not in the paper, that you can improve this by some factor. So if the functions have some, if the Hessian of this function has some property, then sometimes you can make this disappear. But maybe you can ask me outside the talk, but because it's not in the paper, but sometimes this can be improved because this is quite a conservative estimate. Okay, so you can also have this result with expectation, so I skip. And also, so if we had some stronger assumptions, so here we have this stronger assumption saying that the norm of the gradient is bounded below by the distance between the current iterate and the local solution. So then we can also have some linear convergence result, but with respect to the distance, which is a bit stronger than before. But yes, this is exactly the same here. So you have somehow the condition number here, and then this extra factor n over s that appear because of the subspace. And finally, yeah, so quickly, so what about this superlinear convergence? So here, what the assumption that we need is that S is not too close to n. Because of course, if the subspace size is equal to n, then you recover the classical Newton method, and then you have superlinear convergence. So this says that we need some constant C that is independent on the problem parameter, such that S is not too close to n. And then if this is true, so yeah, we have this following theorem saying that we cannot achieve superlinear convergence because we have these things here. So the norm of the solution is bounded below by this quantity. And yes, F, we assume F to be locally strongly convex. So this is very important. So this seems as a, so it is okay. So what is the use of subspace method up to here? So, but because here in the general case, we don't have strong, we don't have this superlinear convergence. So what can we do? But it turns out that, sorry, this is the same with expectation. It turns out that, so if you assume that the rank of the Hessian locally is small, so here this is the Hessian as your solution, x bar. And if the rank is much smaller than n, and if you take the size of the subspace greater than R, then it turns out you can achieve superlinear convergence. So more precisely, so you see here, you have 1 plus delta, and here this is strictly positive. So this is what allows you to get some acceleration. However, the catch is that we should assume that S is greater than R. So it means that we need to be in some kind of Laurent setting. And here maybe there is this quantity that is probabilistic, but you can bound it below. So here this factor is not so important, is superlinear convergence. Okay, so I will show quickly just two numerical experiments to support this. So the first one is support vector regression. So here we just minimize the loss function plus some regularizer. So we use this data set. So UCI, Internet Advertisement dataset. And because the point is just to show how our method works, so we just cut it down. So we consider only 600 samples, and we restrict the number of attributes to 1,500. And we compare with the classical gradient descent and the usual full space regularized Newton methods. And, we take the step size and the parameter as shown below. So yes, so because we're interested in the non-convex case, so this is the loss function is in one dimension, and we consider several choices, but here I will just consider this loss function here, which is non-convex. And so if you look iteration-wise, you can see that the full space Newton method need less iteration. And it makes sense because unless you are in a very specific case, at each iteration, so you move a lot more on the subspace Newton because you are not restricted by the subspace. So you need less iteration to converge to your local optima. However, so if you look at the time, because each iteration is much more costly in the full space method, then what happens is that if you look time-wise, so how the function value decrease with respect to time, we can see that subspace methods are better because here you need some time to compute the direction. And here you see that the dimension is not that high because n is only 1,500. So you can imagine that if we consider much higher dimensional problem, then we cannot use this method anymore. And in the next experiment, it will become clear. So yes, so also now we look at the gradient norm with respect to the time. And you can see that on the full space method, then you have this. It decreases somehow linearly, and then at some point, it just go really fast to the local solution. And this is because of superlinear convergence. In gradient descent, also it's linear, so this is what you expect. And also in the subspace Newton, so you get this linear rate also. Maybe this one, the yellow is purple one is not, but because here we have, I think the rank, I forgot what is the rank, but I will speak about the rank in the next slide. But you can see that this is what we expect. So on the full space, you get this superlinear convergence, but on the subspace method, you only get linear convergence rate. And yes, so another experiment about convolutional neural network. So here we only took a very small one, so only one conventional layer, one ReLU activation, and some max pooling layer, and some so we consider this problem. So here there is no regularization. I will explain why later. And I think the dimension, is also very small toy problem. And we only take a batch of 256 images. And then also what you can see is that, so if you look, let's look at the time directly. So gradient descent decreases very fast, but then it gets stuck at some local minima. Whereas the full space Newton also is very slow. And here, our method converges very fast to the local solution. Also, here it's not so clear, but we made some experiment on some low rank Rosenbrock function just to show that if the rank is smaller than the subspace dimension, then you get this superlinear convergence. I will not show it here, but we tested numerically that if the function has really a low rank structure, then you get some acceleration, this superlinear convergence in our case. So because of the time, so I will go to the next topic really quickly. So here, I just want to say that if the function is not C2, then you can use the Quasi-Newton methods. So basically, what is it? So in the Quasi-Newton method, so here your Hessian is replaced by some Hessian approximation. So HK is some approximation of your Hessian. So basically, if you're not familiar, so at each iteration, you make a one rank update of your Hessian. And so sorry, this is the inverse. This is the inverse of the Hessian. Because in Newton method, you have the inverse of the Hessian. So this is some approximation of the inverse of the Hessian. And at each step, you make some one rank update of the Hessian. So you can compute this very easily. But here, the idea is that we use some subspace methods. So again, what it means is that this matrix is small, and the update is done on the small matrix. So we update the small Hessian using the subspace pk. But otherwise, it's the same thing. So you see, you have the small gradient here. So this is the inverse of the Hessian on the small subspace, and then you go back to the original space. And so here we also try something different. So pk is not really random. So what we did is that we use the previous iterates, an approximation of the previous gradient to build pk. However, the randomness is hidden inside it because here we assume that somehow the gradients are complicated to compute. So if the gradients are complicated to compute, you cannot really build pk easily because you want to add the gradient inside pk to somehow guess the next direction. So what we did is that instead of computing the gradient, we use a random matrix to approximate the gradient. So it means that in pk, you have some approximation of the gradient inside it. So it's not random. I mean, it's not random because we have some fixed direction defined by the gradient, but also there is some randomness because the approximation of the gradient is random. So yeah, this is a bit different from the previous idea. And yeah, so what we do, so we did several settings, but one idea is that if the gradient is really difficult to use, so sometimes we cannot even use automatic differentiation. So here we use, so we call the subspace gradient. So it means that we use some finite difference. And because it's inside the subspace, Q or P, so we use this notation. So just to say this is the gradient inside the subspace defined by P or Q, and using some approximation defined by epsilon. So this is d-dimensional because Q is the subspace, and P, so Q is used to approximate the gradient, and we use D, and M is the size of the subspace. So if it's too complicated, you can just assume that D equal M equal S, the previous parameter. And then, so yeah, so this is a gradient inside the subspace, but we have some approximation epsilon. This is the inverse of the Hessian, so using the BFGS formula, this is the approximation of the inverse of the Hessian. And at each step, we use this matrix. So you see, if you forget about Q, so you have the iterate, the gradient, and this is how we want to guess the best subspace. But we use Q here to get the gradient, some gradient approximation. And what we can have is some convergence result. And yeah, just to say that if we decrease if we take some epsilon that satisfies this condition and that decrease and epsilon k decrease to 0, converge to 0, then you can have some this square root 1 over k rate. So the idea is that if you take smaller and smaller step size, the error due to the epsilon will disappear. So this is just the interpretation you should get. And finally, some numerical experiments. So here we take a larger optimization problem. So also we take the MNIST data set, but we take a 3-layer neural network having this dimension. So this is the size of the dimension of the parameter. And we also did the same experiment on some CNN having this dimension. And here we have some regularizer here. And So we compare the method with the, so in blue, it's our method. Then in orange is the usual gradient descent. In green, this is the accelerated gradient descent. And in red, this is the subspace gradient descent proposed by Cossacks. And yeah, if you look at how the function value decrease, so it seems that our method has the best result. But if you look at the size of the gradient norm, then we lose with respect to the accelerated gradient descent. But yeah, here we have somehow the function value is how the function value decrease. We have better result with our method. And yeah, that's all. So yeah, there is a lot. I mean, it was very quick. I wanted to speak more, but if you are interested, please let's talk outside during the break. Ask me a question if you are interested in this. So thanks a lot.
No, thank you very much. It was very interesting and very condensed, or maybe later I will talk to you again. But regarding the first part,
yes,
all your results assumed that you had some, I mean, that the way you sample those matrices is random, right?
Yes, yes.
I was wondering if there is also, I mean, if randomness is really important, or I'm thinking in terms of, I don't know, you mentioned as a special case this block coordinate type.
Yes, yes.
And you can do, for instance, also cyclic updates, right?
Yes, yes.
Or something like that.
Yes.
Is that also covered? Because usually, I mean, also cyclic, at least in those cases, works particularly well.
So yeah, thank you very much for your question. So I think for the global convergence, this doesn't change so much. However, for the local convergence, the fact that we use some continuous distribution is very important.
Oh.
The reason is that, for example, if you think of the low rank case where we are able to prove superlinear convergence, the proof typically would not work if you use some discrete sample. So even if this is a random coordinate or fixed coordinate, the proof would not work.
I see.
Because here the reason is that we need to use that. So for the Gaussian distribution, this is independent with this is invariant with rotation using orthogonal matrices. And if you don't have these properties, then the proof will collapse.
So it's a local.
Yes.
Yeah, makes sense. Makes sense. Okay. Thank you very much.
There is something more, but maybe we can discuss.
I have other questions, but okay, it may take long.
Thank you for your question.
Thank you very much for the talk.
Hello, good morning, everyone. So I'm here to talk about some splitting algorithms for non-monotone, non-convex optimization, and non-monotone inclusion. So I will first introduce some preliminaries and then present two of our recent works. So just to say very briefly that our team tackles many topics, and among those topics I contribute on bilevel optimization, non-smooth non-convex optimization, and non-monotone inclusion. And earlier today we have already heard about bilevel optimization, and for now I'm going to focus on the last two, non-convex, non-smooth, and optimization and non-monotone inclusion. So these are the main references that I will use for this talk. So to set up everything that we will be seeing today, let us consider a very basic setting wherein you just want to minimize the sum of two functions. Let's suppose for now that they are proper closed non-convex functions, and they are both prox-friendly in the sense that this minimization problem for phi equals f or g is easy to solve or has a closed form. So for these kinds of problems, a very well-known algorithm is the Douglas-Rashford algorithm. And as you can see here, this is where you need the prox-friendliness of the two functions, f and g. So it's quite simple and easily implementable once you satisfy the second condition here. So this is our very basic setting. But what I want to share with you in this talk is how do we extend this algorithm in other instances. For example, if you add two more terms, which are non-convex and maybe non-smooth. And let's suppose that we have a particular setting wherein we have a finite number of functions, sum of finite number of functions, and we only have access to the prox operators. So can we extend again the Douglas-Rashford algorithm for these cases? And lastly, I'm interested in the generalization. So up to what extent can we extend these results? So we will be looking at inclusion problems as well. So for the first part, so just to mention that for the non-convex case, which is what I'm interested in, this is typically a very difficult problem, and only local convergence results are known for the most part, and specifically when you have functions f and g, which are just indicator functions. So they take on the value 0 if you're on the set A or B, and it's infinity outside the set. So basically, that's just saying that you want to find a common point of A and B. So this Douglas-Rashford is only well understood, not really well understood, but most results are only for these cases, but only local convergence result. But despite that, the performance is quite well. So that's some motivation. And the first work to provide a global convergence analysis is the work by Tinke and Goyin. So, but the additional requirement is that the first function f has to be an L-smooth function. So it should have a Lipschitz continuous derivative. And Andreas and Patrinas, they improved the step size estimates for this work using the notion of Douglas-Rashford envelope, which I believe we will be hearing more about later. So I'm going to skip this part. And another result in the non-convex case is not really fully non-convex, but you have a strongly convex function f and a weakly convex function g. So you have a non-convex component, but the overall problem is still convex because alpha, the strong convexity parameter, has to exceed the weak convexity parameter. But of course, in this case, you can just manage to move some quadratic terms and make the function sum of two convex functions. You can imagine doing that. But from a mathematical point of view, you want to understand, will the Douglas-Rashford really work without those modifications that you're doing? So these are the known results. And again, I said that we're interested in the four-term problem, but the motivation for that is actually this one. So let's say that you have now a three-term problem, a famous algorithm called the Davis-Jean splitting. So it extends a Douglas-Rashford algorithm by just adding this term here, over here. So, and Bien and Zhang were able to apply Tinke and Goyin's technique to establish global convergence for this case. And the additional assumption here is that H is an L-smooth function as well. And overall here, the assumptions require that both f and h should be smooth functions. So, but when you look at the literature in non-convex optimization, what you will often see for three-term problems is that the last component is usually non-smooth. So for example, this part could be a DC function. So there you will have probably two non-smooth functions. So that's actually our motivating problem. So what if the third term is non-smooth? Let's say, let's replace it by P. Then what can we do? Will the Davis-Jean splitting algorithm still work? So then now we consider a non-smooth setting, but motivated by this kind of condition. So if H is LH smooth, it is well known that this function is a convex function. And now I'm just going to borrow the half of this. So I'm going to assume now that P is a non-smooth function that mimics half of the above property. So let's just say that the minus part is convex. So in other words, the function is weakly concave. So in that case, we were able to come up with this algorithm, which is, for now, it doesn't look very similar to the original algorithm. But if you consider special cases, for example, if LP equals 0 and you set the parameter beta to infinity, then the algorithm will look like this. So it's still the same format. So this is same as the Davis-Jean splitting. You have y, z, x iterates. But if you compare the z iterates, then the only difference is on this part. For the Davis-Jean splitting, this one is just the gradient of the smooth function h, the third term, evaluated at the previous point yk. But this time, it's a lot more different. But now, so now we have come up with an algorithm which will work if your third function is non-smooth. So, but then we realized that when you study the convergence of this algorithm, then everything will still work even if you add back the original function h earlier. So that's actually the main reason why it became a 4-operator splitting algorithm. So we just realized that, oh, why not just put back h? Anyway, all the analysis will still be the same. And in that case, it's still nice because you can still reduce to the Levisian splitting later as you wish. And informally, we were able to show that the y sequence will converge to stationary points of the problem if the step size is sufficiently small. So this is the important takeaway from this result. So notice that it's in terms of the yk, not really the xk. So usually we call that like the shadow sequence. So since this is quite a general algorithm, then you expect that if you just choose particular functions f, g, h, and p, then you will get the well-known algorithms that you know. That, for example, if p is 0, you get the Daviscian splitting. If f and h are both 0, then you get Brock subgradient algorithm. And if f is 0, kappa is 1, beta is infinity, then you get the proximal DC algorithm. So it's quite nice in the sense that you were able to capture many algorithms, and all the convergence are contained in this result. And what can we say about the performance of this algorithm? So one of the things that we were able to do is to derive larger step size, thanks to the technique by Andreas as well. So it's motivated by that technique. So these are some works which also study the Daviscian splitting. So Bien and Zhang, Dao et al. So they also studied the Daviscian splitting algorithm, but their estimates were quite conservative. So you can see here the benefits of larger step sizes that we were able to derive. So this is a nice contribution, I think. And in terms of solving problems like this, let's say you have now a 4-term problem, we compared our algorithm with the famous proximal DC algorithm, and we were able to show that this parameter here, this is the kappa that you see in the x iterate, the definition of the x iterate, and as you can see, that's a lot of improvement over the famous PDC algorithm. So those are the main contributions of this particular project. So now let's move on to the multi-operator inclusion. So we're interested in solving these problems, but now I want to focus first on the third one. So let's consider first a more general problem, and then later let's specialize the results to the optimization case. So consider this 2-operator inclusion problem. Find x in H, where H is a real Hilbert space. So here, this can be infinite dimensional. I don't require finite dimensionality. And you want to find x such that 0 is in A of x plus B of x. So we're interested here because imagine you're minimizing a function f plus g. So if you want to find stationary points of that particular problem, minimize f plus g, then you're basically looking at the zeros of the subdifferential. And provided that the subdifferential is distributive, then you can imagine that A is just the subdifferential of f, and B is just the subdifferential of g. And it has some nice connection with your optimization problem. So you can view this as a generalization or a more like a high-level setting for studying optimization problems. And earlier, we required, when we introduced the Douglas-Rashford algorithm, we required that the functions are prox-friendly functions. And this time, since we're considering a more general setting, we require A and B to be resolvent-friendly functions. So in the sense that calculation of this particular function is easy. So by the inverse here, so this is the identity map. So the inverse here, that is not the traditional inverse, but basically the inverse of the map. So you can imagine you have a set-valued function, you just switch the x and the y, the input and the output, and you can still get the graph. So that is the inverse of a function. So, and your algorithm in the most general case will look like this. So this is the Douglas-Rashford algorithm. More strictly speaking, this should be element. So unless those resolvents are single valued. So for example, if A is just the subdifferential of F, the resolvent will just go back to your proximal mapping. So this is just the same as what you have seen in the introduction. So now, mostly, when you study Douglas-Rashford algorithm in this case, you require some monotonicity properties. So by monotone, it means that this inner product is non-negative. You can view U and V here as just AX and AY. So in particular, taking specific elements because they could be set valued. So that's what we mean by monotonicity. And it's maximal if you cannot extend it to a larger graph, which is still monotone. And for example, if F is a proper closed and convex function, then it's well known that the subdifferential of F is a maximal monotone function. So this is a very famous result and an old one. So if your functions A and B are maximal monotone, then you get the weak convergence. So remember that we're in the infinite, we could be in an infinite dimensional setting. So the iterate xk is weakly convergent to some point in the set of fixed points. And you also have the weak convergence of the shadow sequence yk to a zero of the original problem. And when you replace A and B by subdifferentials, then you can also get nice results in terms of optimization. Now, our main question now is that what if A and B are not maximal monotone? So up to what extent can we extend this? So we have seen some special cases already. So as I've said, you can consider the optimization problem, set A and B to be the subdifferentials, and these are the results that we already know. But this is in the context of optimization. So we have the alpha convex, beta convex function, such that the sum is still strongly convex, and this is the first work I showed earlier. And we want to extend this to more general setting. So luckily, alpha convexity, so this kind of notion here, this is easily extendable. So it has a natural extension to operators. So for instance, we can define sigma monotonicity as follows. Earlier, you've seen the right-hand side to be 0, but this time we relax it by this quantity, sigma times the squared norm of the difference of the inputs. And the sigma here could be positive or negative. So it's a relaxation of monotonicity if sigma is negative. So equivalently, this means that A minus sigma times the identity map is monotone. And we define maximal monotonicity in the same way. So for this setting, Dao and Pan, they were able to show that, so this is a generalization of what we've seen for optimization, that if the parameters alpha and beta sums to a positive number, then if the step size gamma is sufficiently small, by that, it's sufficiently small because this quantity is negative if alpha plus beta is greater than 0. So if gamma is sufficiently small, then you get a result which is very similar to what you've seen for the maximal monotone case. So this is only this time this is a nicer result because you now have strong convergence. Nicer result if you look at the infinite dimensional setting. Now, can we extend this result to more than 2 operators? So that's what we want to find out. So at first, what would be your Douglas-Rashford algorithm if you extend it to more than 2 operators? So let's recall a little bit the traditional way of doing this. So this is our target problem. You have, you're finding x such that 0 belongs to the right-hand side here. But now m could be greater than 2. So the traditional way to come up with the Douglas-Rashford algorithm is to still force it to be a two-operator inclusion problem. So still write it as F plus G. It's still a two-operator problem. But F and G are constructed as follows. So at F, you include the information about A1 up to AM, all your operators. But look at the inputs here. So A1 of X1 up to AM of XM. And G is just the normal cone to the diagonal set. So DM is just the set, a subset of HM wherein the coordinates are all the same. And here, the normal cone is just what you would do in convex analysis is apply the definition and you will come up with the following. So the normal cone is just the set of all W's such that the sum of the coordinates is equal to 0. So it's easy to see that if you just follow the definition of this, that if 0 belongs to this set, then it still solves the first problem over there. Because the 0 must have equal coordinates, and then that equal coordinate will be the 0 of the original problem. So I hope that's clear from here, but we can discuss later if you want. And since this now is a two-operator problem, you can now apply the standard Douglas-Rashford algorithm because the resolvents for this function are easy to compute. And the Douglas-Rashford algorithm will look like this after applying the definition of the resolvents. So here, G is fixed to be a maximal monotone operator. So if you look at the definition of G, it doesn't encode any information about A1 up to AM. It's fixed to be just the normal cone to the set DM. And this is not, in that sense, it is not compatible with the generalized monotone operator framework because it's nicer if there's a balance of monotone and non-monotone functions. So here, but in this kind of formulation, the second function is fixed to be maximal monotone. So there's no room for doing some more analysis wherein you have weakly monotone operator. So fortunately, there's this another reformulation by Campoy. So it looks very similar, but if you look at F this time, you only encode the information from A1 up to AM minus 1. But now the AM, you put it as an additional term for your second function G. So where the K here is where you need the AM. You make, it's almost making M minus 1 copies of the AMs, but all of them are evaluated at different points, X1 up to XM minus 1. So this is nice because the lifting is, this should be M minus 1. So compared to the original reformulation earlier, the lifted space is M-dimensional. And this time, it's only M minus 1. Here, M minus 1 dimensional. So this should be minus 1. But I should say that this reformulation by Campoy is only valid if the set valid operator AM is convex valued. If you investigate more closely. So just some rough computations. So if 0 belongs to the f of x plus g of x, following the definition of k of x here, then you have the following. So x is in the diagonal set, dimension m minus 1. You can find u and v such that negative u plus v is in this normal cone. And remember that in the normal cone, you have to, for it to be in the normal cone, when you add all the elements, the sum will be 0. So if you add all the coordinates, this is what you're going to get. And the ui's here, u1 belong to a1 of x, um minus 1 belong to am minus 1 of x. Each vi here belongs to am of x. And for this to be really something like a1 of x, a2 of x, up and so on and so forth, this should be in am of x. So that's why, in hindsight, your am should be actually convex valued for this to be a proper reformulation. So, but there's an easy fix for that. So we just redefine K in such a way that its domain is only the diagonal set. And then you just force to take any element of AM of x1 or x2 because they're just equal anyway. And then you force that to be the representative for each coordinate. So you don't really have to worry anymore about getting the sum to be in the set. And in that case, then if the sum of the weights is just 1, then you still have a nice reformulation. So zeros of the reformulation is just m minus 1 copies of the zeros of the original problem. So you still have a valid reformulation. And luckily, if you look at resolvents, so just this is very similar to what we had earlier, just some scaling, then we were able to show that they are very easy to calculate, actually. So you can apply the Douglas-Rashford algorithm as you wish. And in terms of the components, you have the following. And we were able to show that still, if x is a fixed point of the defining operator, then the shadow of the fixed point is corresponds to a 0 of the optimization problem. So that's nice. And now, so we were able to find an alternative reformulation. We have the Douglas-Rashford algorithm. We have this correspondence. And what can we say now about the convergence of the Douglas-Rashford algorithm? So our assumption this time is that each AI is maximal sigma I monotone. And our conjecture is that we will get convergence if the sum of the moduli is strictly positive. So that's a conjecture for now. And fortunately, we were able to show that F and G are maximal sigma monotone operators as well. And you can just apply the theorem I showed earlier for two operator case, and you can get a nice theorem like this. But so you don't mind the details here, but the only point is that the sum of the moduli is strictly positive. But if you compare that with our conjecture, so this is what we had in the previous theorem in the m equals 3 case, and our conjecture is actually a wider array of parameters like this. So it's not really the same as what we expected, but because we just directly applied the existing theorem. But I will not show all the calculations, but still we were able to show that if you do more rigorous work, that you can actually show that your conjecture is true. That if the sum of moduli is strictly positive, then you get the result. So we were able to cover everything here in this picture. And for non-convex optimization, this is what you're going to get as an extension of Douglas-Rashford algorithm. And this is just an instance of that, because remember, everything here were resolvents, but in general, you only have this inclusion. So, and recall that this is what we had for the m equals 2 case. And if you just consider the sigma I convex setting, then you can just use the previous theorem that I showed. Then you have now the result for the sum of m functions case. But what about this second condition? So in the second condition, we need more assumptions, and we need to work on a finite dimensional setting. And notice that unfortunately here, we require that all the m-1 functions are L-smooth functions. But fortunately for the last function, it's proper and closed, and you need the objective function to be coercive. And we get, this just says that you have stationary points, just like in the m equals 2 case, provided that the step size is sufficiently small. And the proof techniques doesn't rely anymore on the monotonicity, Feher monotonicity of what you can do in operator case, but rather uses a merit function, which is again based on the envelope, an extension of the envelope in the m-dimensional setting. So to summarize, we were able to do what I showed in the introduction earlier. Thank you very much for listening.
Thank you very much. It was really a fascinating talk. I was interested in a limiting case. So both in the previous theory, but also in your results, you have to assume that the sum of the, let's say, the sigma i's is strictly positive. Do you have a counterexample? I mean, do you know if that you can, if it also works, if it is greater or equal than 0, so that you recover also the standard setting, or if you have counterexamples where you have, for instance, one which is, I don't know, minus alpha I weakly monotone, and the other one is, sorry, minus alpha weakly monotone, and the other alpha strongly monotone, so that they sum up to 0, but do you know if the algorithm doesn't work in that case?
So I don't have a counterexample, and I believe the algorithm should work in that case. And I'm aware that in the optimization case, if the sum is 0, then you can show that the convergence will still hold if in the setting that you considered. But in the operator case, I'm not sure yet if it will work, but I suppose it should work.
Yeah, because it would be nice to have, because then it would unify the analysis, right?
Yes,
because
yes.
Otherwise you have to use two different techniques for the,
Yes.
let's say, for the monotone case or for the weakly monotone case.
That's right. But there's also a way to just perturb a little bit the iterations. So just introduce some coefficients. And then some people call it the adaptive Douglas-Ratchford algorithm. And just by some minor tuning, minor perturbation of those parameters, then you can cover the case that you exactly see. So just perturb Douglas-Ratchford algorithm.
I see.
So I think it will still work in the classical set.
Very interesting. Thank you very much. Thanks.
Thank you. Okay, Jinpei, please. Okay.
So I also have a question about the last part. So you need the summation to be like larger than 0. So do you have real examples that there are some of them are negative, and then one is positive enough to make the sum really larger than 0? So what's the motivation of developing that?
So there's an example for the case m equals 2. So in image denoising problems, there's an example like that. But unfortunately, for that example, the first function wherein you have the strong convexity, it's actually, it can be written, because it's separable, so it can be written as a sum of a finite number of functions, and you still satisfy the assumption. So the next question would be, is there a benefit to like considering those as separate blocks instead of just considering it as one block? So that's the only example I can think of for now. But I think the follow-up question will be that, like, is there a benefit if you really just break them down into different components? Because you're already sure that the sum will be strictly positive. But is there a benefit in doing that? I don't know.
Thank you.
Thank you. Okay.
Yeah, I'm a fourth year PhD student in Subspace Institute, Berlin in Germany, in the group of Sebastian Pokutta. And yeah, so I've worked on different problems in optimization, but I've focused on Riemannian optimization in my PhD. All right, so this talk is based on a collaboration with my professor Sebastian, of course, and David, who used to be a postdoc in our group and is now a professor in Madrid. Right, so this talk is about online optimization on Riemannian manifolds. So there's these kind of two topics, and I'm going to shortly introduce both of these topics for you. So online optimization and then Riemannian optimization. And then I will kind of bring them together to show you some online Riemannian algorithms. Okay, right, so what is online optimization? So online optimization is usually phrased as a game between a learner, so that would be the algorithm that would be controlled by the algorithm you want to design, and an environment. And so this game is repeated for multiple rounds, and in each round, the learner will select some action xt from some set of actions x, and the environment will then reveal a loss function lt. And so what's important here is that the loss function is revealed after choosing the action, right? And so this loss function can be, it will satisfy certain regularity conditions like convexity or Lipschitzness, but other than that, it can be anything, right? It can even be adversarially chosen by the environment. And so after the environment revealed its loss function, the learner will pay a loss xt. So one simple example of this could be SGD, right? If LT is a loss function that comes from sampling some random variable, then you just recover SGD. If LT is the same variable, if LT is the same loss function every round, you just get classical convex optimization, right? But here we are in a more general setting. And so the goal of the learner is to minimize the cumulative loss, right? So the loss it pays in every round. And in order to kind of be able to gauge how good a learner performs, we will measure this in terms of regret, which is the cumulative loss of the learner compared to the loss of playing one fixed action. And we call this action a comparator, right? So that would mean not a sequence of actions like the sequence xt that the learner chooses, but just one fixed action that also lies in the same set X. Okay, and so classically, this would be solved by some variant of online gradient descent. So this is essentially just the same as gradient descent, just that the loss function changes at every step. So it's LT instead of L. Under like standard assumptions, the function is convex and Lipschitz, and the set X is compact and convex. We can show that the regret grows no faster than square root of t, right? So, and this is also tight. So this is kind of the best we can do, right? If you think of offline optimization, we would kind of divide this by t, right? We would have like this average regret, which would coincide with the classical convergence result of 1 over square root of t. Okay. So in this setting, in this fully adversarial setting where LT can be anything, we cannot do better than square root of t regret. But of course, in reality, the environment is usually not fully adversarial, right? Even if there's an adversary, maybe the adversary is not perfect, or there's a part that's adversarial and a part that's not adversarial. And so in this setting where we can make some predictions about the environment, we could actually do better. And how we will do this is we will encode some knowledge that we have about the system in a so-called hint. And the hint is essentially a function that approximates the future loss function. So if the future loss function is LT, then the hit would be tilde LT, right? And so again, we've got the same game, only that before the learner selects an action, xt tilde in this case, right? It can observe this hint and do a kind of second update. And so the algorithm for that is just that, right? The first line here is exactly the same I've shown you before. This is just online gradient descent. And then instead of choosing SC+1 as the action, you take an additional gradient step on this hint function and choose that as an action. And so if we use these algorithms, then we can show a regret bound of d squared over eta, where d is just the diameter of the set, eta is the step size, plus eta times vt. And this vt is the kind of important thing here. This is usually referred to as gradient variation. And what it does, it is just measures how good is our hint. And it measures this specifically via the gradients, because the gradients are exactly the information we're using, right? In the algorithm, we're using those gradients. So imagine that the hint is exactly the future loss function, right? You can kind of look ahead. Then this becomes 0, and then we get constant regret, right? So this would be the best case. In reality, that's of course not, will often not be the case. But essentially, whenever our gradient variation grows slower than O of t, then we can hope to improve our regret beyond square root of t. Okay, so this is just a very brief introduction into online optimization. And sorry, I forgot to mention this. Using these hints in order to predict the environment is usually referred to as optimism or optimistic algorithms. So you're kind of hoping that your prediction is good, so you're optimistic. All right, so that was just a quick introduction to online optimization. And now I'm going to give you also a quick introduction to Riemannian optimization, right? Because afterwards I want to do Riemannian optimistic optimization. So by Riemannian optimization, I just mean that you're optimizing functions where the domain is a Riemannian manifold, right? Instead of, say, Rn or Hilbert space or whatever. And in this case, we assume about the Riemannian manifold that it's uniquely geodesic. That means that between any 2 points, there's just one geodesic. So geodesic is just like the shortest path between 2 points on that manifold, and that the sectional curvature is upper and lower bounded. This is also a quite mild assumption. And so one example of so the sectional curvature kind of tells us how curved is our space and in what direction does it go. So for example, this here is a hyperboloid. This has sectional curvature -1, and this is a sphere. This has sectional curvature +1, right? And specifically, the results I will show will be for Hadamard manifolds. And so those are manifolds that have non-positive sectional curvature. So this would include, for example, the hyperboloid on the left, but not the sphere. Okay, so why is Riemannian optimization interesting? We'll give you two kind of main reasons. The first one is that you can use geometric properties of your problems. So there's a lot of problems, kind of Euclidean optimization problems, that have constraints that have some specific geometric structure. So for example, if you want to do low-rank matrix factorization, that leads to this kind of complicated non-convex constraint, but the set of matrices with a fixed rank create a manifold. And so now you can transform a problem with complicated constraints into an unconstrained problem where the domain is just a manifold. So there's a lot of examples here. One other one is, for example, maybe training neural networks with orthogonality constraints. That was shown to help a lot for a recurrent neural network. And so having this orthogonality, you can encode it by optimizing over the Stiefel manifold, which is just the set of matrices, just the matrices that are orthonormal. Another point that is maybe less well known is that Riemannian optimization can also help to improve the problem structure. So there are problems, Euclidean optimization problems, that are non-convex, but when you phrase them as optimization problems on some manifold, they become geodesically convex. And I mean, geodesic convexity is just a generalization of convexity to manifolds. And so one famous example is operator scaling. Okay, so if this was a bit too abstract, I'm just going to give a very brief example. So of how Riemannian optimization could work. So let's say you want to compute the maximum eigenvalue of a matrix A, then that is equivalent to maximizing the Rayleigh quotient. And we know that the Rayleigh quotient is scale invariant, right? So instead of maximizing over all Rn, we could just maximize over the unit sphere. And so the unit sphere is a non-convex constraint. However, the unit sphere is also a Riemannian manifold. So now we can write a Riemannian optimization problem instead of a Euclidean one without constraints. And so, I mean, this was mostly for illustration. I'm not claiming that this is better than, I don't know, power iteration or Langsos, but this actually works, right? So this optimization problem has some local convexity, or actually so there's a generalization of convexity called quasi-convexity. And so we have some local strongly quasi-convexity for these functions. And so that means that we can solve them with Riemannian optimization problems, for example, something like Riemannian gradient descent. Right. And so what is Riemannian gradient descent? I mean, in this slide, I'm really trying to give you like the shortest possible introduction to Riemannian geometry that you need for Riemannian optimization. For those that know about these things, this is super superficial, but I'm really just trying to give you a broad idea. So I said that in Riemannian optimization, you're trying to optimize over the domain, which is a manifold. So our iterates xt, they rely on some manifold, M, and then at each point, you can define a tangent space. The tangent space is just a local linear approximation of a manifold that is a vector space. And then at that point, you can compute a Riemannian gradient. And so in most applications, the manifolds we're considering, they're embedded in Rn, right? Or in some ambient space. And so in that case, what is the Riemannian gradient? It's just the definition, the projection of the ambient gradient projected onto that tangent space. I mean, this is just a specific case, but it's very important for applications. And then you have the problem that you have a point on the manifold xt, and you have a gradient which lives on the tangent space, right? So you cannot just, as in the Euclidean case, do addition, right? So you want to move to another point in the manifold. And how do you do this? You do this with an exponential map. So the exponential map just takes a point on the manifold, and it takes a vector in that tangent space, and then it moves in the direction of that vector along a geodesic. So this was a very superficial introduction, of course, of this. This operation can actually be quite expensive, but for some manifolds like the sphere or the hyperboloid, it's also given in closed form. And then lastly, I've said before that we are assuming that the manifold is uniquely geodesic, and that means that we can actually invert the exponential map. And so we have this thing called either inverse exponential map or logarithmic map, which is just the inversion of the exponential map. So that would mean, okay, I have a point xt and I have a point xt plus 1. What is the gradient in the tangent space of xt such that if I apply the exponential map to it, I land at xt plus 1? Right, so these are like this is the basic working of Riemannian gradient descent and the most important geometrical concepts that we need for this. And so here's one last slide about Riemannian geometry, and that's quite important. So if you want to prove gradient descent type proofs, usually you will use the cosine inequality in the Euclidean case. The problem is that this inequality, this equality does not hold in Riemannian manifolds. Rather, it becomes an inequality, right? So I've tried to write these things kind of analogously, right? So on the top, we've got the scalar product, and on the bottom, we've got the scalar product in the tangent space of xt, right? So this here is just the vector from xt to xt plus 1 in the tangent space. This one is the vector from xt to z, another point in the manifold in that tangent space. And then you upper bound it by these distances. And what's important to see is that we get this term zeta d that pops up. And this zeta d is a term that depends on the diameter of the triangle and on the sectional curvature. And you can think of it essentially as a way to measure how much deformation we're getting by the nonlinearity of the manifold. This is kind of informal, but I think this is not too bad. Another way to look at it, and that will be important later on, is that the squared geodesic distance is zeta d smooth, right? So in the Euclidean case, the squared distance is 1 smooth, but in a Riemannian manifold, it becomes zeta d smooth. So the smoothness of the distance function depends on the geometry of the manifold. Okay, right. So now I've introduced online optimization and optimism and Riemannian optimization. And now I'm going to get to the meat of this talk, right? So Riemannian optimistic online optimization. Okay, so just a quick reminder, right? In the Euclidean case, we can get this regret bound of d squared divided by eta plus eta times vt, where d is the diameter of our set, eta is the step size, and vt is this term that approximates how good our hint was. So here's a first result by Wang et al. From 2023. That one works for general manifolds. By general manifold, I mean it could have positive or negative sectional curvature, and it does not impose any constraints. So here, the notation, I'm sorry, is a bit off. I left it like this for brevity, but d is now not the diameter of the constraint set, but it's the diameter of the optimization domain, essentially. And so there's two new terms that pop up in this analysis. One is the zeta d term, right? So here we are kind of have a bit worse regret that comes from the geometry, and we have this g squared, which is just the Lipschitzness of the function. The issue with this work is that when you choose the step sizes, you get a recurrent relationship between d, which is essentially the diameter of all the points where the iterates go, and the step size. And in this work, they actually assume that the iterates lie in a bounded domain, which in some cases is actually a reasonable assumption for some application that they're using, but in general, you cannot do this. I mean, you can assume it, but it's not in general given that this is the case. So there's this problem in general. And then there's a second work, and this work is only in Hadamard manifolds, so manifolds with non-positive sectional curvature, and this actually does use constraints. And the issue here is that, so as I've shown you before, for optimistic methods, usually you have a method that has like these two iterate sequences, and in their case, they project one of these iterate sequences onto the set X, and the other one, they only project onto kind of a reduced, an extended version of the set. We call the set X tilde, and you can think of it as the following. Let's say you're inside X, and you take one gradient step, in this case on the hint function, then you are still in X tilde. So this is exactly the definition of X tilde. It's just kind of an extended version of X. And so this leads to a kind of weaker regret guarantee, which is called improper regret, where they're saying, well, the actions the algorithm takes lie in X tilde, so this extended set, but we compare to actions that lie inside of X, the smaller set. So it's not exactly clear how kind of how improper regret relates to classical regret, but it seems like it's probably worse. And another problem that you get here, again, is this kind of recurrent relationship between eta and d tilde. And here it's even easier to see, right? Clearly, the definition of X tilde depends on eta, and eta will also depend on d tilde. So there's this kind of recurrent relationship here. Right, and also there's a zeta term from the geometry coming up again in the regret bound. Okay, so before I will introduce the algorithm we came up with, I just want to say a quick thing about where these problems come from. So the issue in Riemannian optimization is that metric projections on Riemannian manifolds are very hard. So a metric projection is just, I have a point outside of some set and I want to project it to the closest point inside a set, right? And if you have positive curvature, if you're, let's say, on the sphere, then the projections are not even non-expansive. So that makes the analysis of algorithms using such projections really hard. And even in Hadamard manifolds, so manifolds that are, have non-positive sectional curvature, the first full proof without any strong assumptions of projected gradient descent on manifolds, so projected Riemannian gradient descent, is from 2023, and it's actually a work from me and my collaborators. So that just goes to show that proving convergence of these algorithms theoretically is kind of hard. Right, and so this is where a lot of these problems come from in online optimization. And the solution we are proposing is an algorithm we call RIOT, so Riemannian implicit optimistic online gradient descent. And the key point here is that instead of linearizing the function, so taking gradient descent steps on the loss and the hint function, we are taking steps on the full function, right? So this is a solution that in general is not given, right? This is an implicit update. That's where the implicitness comes from. And so here's our result, right? For Hadamard manifolds and compact-convex sets and geodesically convex and differentiable functions, loss functions and hints, we get this regret bound, which is, and the central thing here is we can handle constraints, right? So we can always ensure that our iterates lie in our constraint set, and we don't have this recurrent relationship between the step size and the size of the constraint set. And another nice side effect is that actually we don't have any dependence on zeta, right? Zeta is this term that measures the geometry, how much the geometry, well, that depends on the geometry of the manifold, sorry. So we have kind of solved this problem with the constraints, and we have improved the regret bounds. So now you could say, well, okay, this is nice, but I mean, that requires solving potentially quite hard problems. So this does not actually impact the regret, because the regret is independent of the complexity, but still, that's quite a strong assumption. And what we were able to show is that if our loss functions and hint functions are in addition L-smooth, so L-smooth, by this I just mean that the function, their gradients are Lipschitz, then we have an inexactness criterion. So we can say, okay, if we have an epsilon approximation to our problem, that's where epsilon is small enough, then actually we stay with the same regret guarantee. Okay, and another advantage of assuming smoothness of these losses is that we can actually now solve these subproblems that come up in every iteration of RIOT relatively cheaply. Because, so we have a loss function that's L-smooth and G-convex, and now we add this regularizer, which, as I've said before, right, it's not 1 over eta smooth, as it would be in the Euclidean case, but it's zeta over eta smooth, and it's also obviously strongly convex. And so I mentioned this in an earlier slide, right? We have a projected Riemannian gradient descent method that converges linearly, assuming smoothness and strong convexity. And it's linear, but it still has a dependence on kappa, which is the condition number of the function, and zeta, which is the comes from the geometry. So if we now plug in what we know about the function, we get this condition number of L eta plus zeta. And now if we plug in this condition number into this result, we get the full complexity of computing one of these Riot steps. And since usually we take step sizes that look like 1 over L, sorry, what you get is something like zeta squared. So this is nice, right? We can converge quite quickly, but we can actually do even better. So when I say we can do better, then I mean in terms of gradient oracle complexity. So in the Euclidean case, this is also a relatively well-known thing, right? If you have a composite function, then you can do a bit, and you can use this composite structure of the function. You can do better than classical gradient descent. And the idea here is, if you have a function that's composite, right, that's composed of a function f and a function g, then you can, instead of linearizing the whole function, which would be gradient descent, you can just linearize one of these functions, right? So f you linearize, so you do something like gradient descent, but g you don't linearize. So this is more akin to proximal points. So it's kind of a hybrid version of these. And then you don't depend on the full smoothness and the full strong convexity, right? That's not your condition number, but the condition number would be the smoothness of f and the strong convexity of g. And so in our case, that would be the smoothness of LT and the strong convexity of our regularizer. And the nice thing about this is that now we don't suffer from the smoothness which depends on the geometry that I've mentioned before, and our complexity just becomes L times eta. And since usually we take a 1 over L step size, this just gives us O of 1 up to some log factors. The only issue with this is that, so we have not figured this out yet fully, but solving this problem could be hard. So we cannot show that in general this is a geodesically convex problem. It could be for some manifolds and some problems, but we don't know yet. So it is well defined in the sense that it's a compact set. So there is a minimizer. You can actually solve it, but in terms of computational complexity, this might be a bit hard. But still, it only requires one gradient computation per step. So in terms of oracle complexity, this is much better. Okay. Okay, so now I've shown you this algorithm Riot, which is optimistic and works for the online setting. In the Euclidean case, there's a well-known way to use these algorithms to get faster algorithms for min-max optimization. And now I'm going to do just that for the Riemannian setting. So by Riemannian min-max optimization, I mean that we have a function f in x and y, where you want to minimize it in x and maximize it in y. And it's g-convex in x, g-concave in y. And then we have these convex compact constraints, and the function is also smooth, right? And this has several applications. So one specific one would be distributionally robust linear quadratic control. But in general, this works for any finite sum minimization problem, Riemannian minimization problem. You could also phrase it as you can robustify it via a min-max formulation. So there's a couple of applications here of why this is interesting. And so the idea is the following. You take your online algorithm and you implement it twice, once for x and once for y. And so one player is trying to minimize it, the other player is trying to maximize it. And we call this algorithm RIOTA for Riemannian implicit optimistic gradient descent ascent. And it works as follows. So we define a sequence of losses that is based on the actions of the opposite player. So what the minimizing player receives f, which is fixed in terms of the action of its opponent y, and the maximizing player receives the same loss function, but fixed in terms of the action of the other player. So it's negative here because the maximizer, of course, wants to maximize the function, so it wants to minimize the negative function. And then as hint functions, we give the same function, but where it's fixed with respect to another action, right? So Riot has these two iterate sequences. One is xt tilde or yt tilde, and the other one is xt or yt. And so intuitively, why does this work? This works because each player is really playing against an adversary, but this adversary, it also knows that the adversary is using some gradient-based algorithm, right? So this opponent has some stability. It will not choose one action in one round and a completely different action in the next round, right? It will choose something that's kind of close to it. And so to quantify this kind of difference, we can just plug in the definitions and see that we get a gradient difference. And since our functions are smooth, we can just upper bound the space smoothness, the distance between those two iterates, right? So in this case, yt and yt tilde. And under these standard assumptions, we can actually show that Ryota obtains an epsilon solution in LR squared divided by epsilon iterations. So here L is the smoothness, R is the initial distance of the iterates to the saddle point. Right, and epsilon is the suboptimality in terms of the function value. Okay, so in contrast to online methods, we are interested now in the full gradient complexity, right? So we cannot just say, okay, this is the amount of iterations we're doing of Ryota. We want to know, well, how much gradient calls does each iteration cost, right? And so I've shown you before that using either PRGD, so projected Riemannian gradient descent, or composite Riemannian gradient descent, we can actually implement these update steps. And now we want to have the full complexity by also taking into account the complexity of each of these steps. So if we implement Ryota with PRGD, then actually for this constraint setting, we have a large improvement over the prior best results, where the zeta constant, which comes from the geometry, is improved from zeta to the power of 5.5 to zeta squared. Also, we dropped the requirement of knowing the initial distance and the Lipschitz constant in this constraint set, and the algorithm is much simpler. So the algorithm I've shown you, it consists of write, which is these proximal or implicit steps, and implementing each of these steps. So we have 2 loops, whereas the prior method required 5 loops, which is much harder to implement. Right, and so if we implement Ryota with CRGD, which is this composite method I've talked to you about, we actually recover the Euclidean gradient complexity, right? So up to some log factors, we really have the same rates as in the Euclidean case. So there's no, up to some log factors, there's no dependence on the geometry of anything. And when we proved this result, we were quite surprised because there's a lower bound in the minimization case. So if you want to minimize a convex and smooth function on a manifold, then we know that it takes at least zeta steps or zeta gradient calls. So this is a fundamental result that kind of shows there is always some hardness that comes from the geometry of the manifold. And I mean, of course, okay, so minimization is a special case, minimization is a special case of min-max, right? If you just fix the max, put it to 0 or something, then you have a minimization problem. So this lower bound also holds in our case. So just for comparison, right, I've said that this is our rate. And so it might seem like there's a kind of disparity here. Maybe our upper bound is wrong or the lower bound is wrong or something. But it turns out that this is not the case. The point is that the lower bound was constructed for a function in hyperbolic space. And in hyperbolic space, it turns out that you can upper bound the primal gap by L, so the smoothness, times the distance between the optimizer and your point, distance squared, sorry, divided by zeta. In the Riemannian case, there's no divided by zeta, right? It's just the smoothness and the distance squared. And so, right, rewriting this with an epsilon, right? If epsilon is our primal gap, we get that epsilon is O of LR squared divided by zeta. And if you plug this into our rate, we can see that actually our upper bound is actually larger than the lower bound. So those 2 results do not contradict. They actually, yeah, they don't contradict. And so what this means is that there is some fundamental hardness from the geometry. It's just that it's kind of implicit in the upper bound. You just don't see it explicitly. And what this means is also that our upper bounds and the lower bounds, they match up to log factors for Riemannian min-max problems. And that's actually quite surprising because even for G-convex minimization, arguably a more fundamental problem, the upper and lower bounds don't match. But for min-max optimization, we were actually able, I think for the first time, to have matching upper and lower bounds up to some log factors. Okay, so to conclude, I introduced Riot, an inexact implicit optimistic algorithm for constrained Riemannian optimization on Hadamard manifolds, which was able to address limitations of prior works. And it also matches the best Euclidean regret bounds. And using Riot, we were able to design a min-max algorithm for G-convex, G-concav, and smooth min-max problems on Hadamard manifolds, which, if implemented with CRGD, are able to have matching upper and lower bounds in terms of the complexity up to some log factors. And if we implement it with PRGD, then it improves the rates and relaxes the assumption compared to prior works. All right, thank you. That was it.
Are there questions from the audience?
So you mentioned that lower bound and the last topic. So you mentioned that the lower bound and upper bound match. It was the first the first result in this area. So is it also first for Euclidean setting?
No, because in the Euclidean setting, so this lower bound is for Riemannian optimization, and for the Euclidean setting, the lower bound is also LR squared divided by epsilon. So this has been solved since, for a long time, I would say. There's one extension which is for problems that are strongly convex and strongly concave, where the strong convexity and strong concavity for X and Y are not the same. There is actually still an open question whether, so there's no algorithm that has matching upper and lower bounds. But for this general assumption of convexity and smoothness, this is optimal.
Okay. So you pointed out when you think of Riemannian setting, there is some difficulty, like a projection that's no hold in general or something like this. So when you did this work, what's the obstacle or difficult part for you to deal with this kind of thing in a Riemannian setting? What's the difficulty?
So the difficulty, if you take the prior works and you try to do it explicitly with projections, at least for me, I have no idea how this would work. This is related to multiple things. One important thing is there's always this question of where you linearize the space, right? If you linearize the function at two different points, in Euclidean space, that will give you two affine functions. But in the Riemannian setting, these two functions are defined with respect to different tangent spaces. So they are not convex anymore. And so what we did here is essentially that we knew we can solve these subproblems in the offline setting. And we leveraged these methods to have the implicit ones where, if you look at this algorithm, essentially the projection is kind of hidden in here. You just assume that it works. And when you assume that, then you can actually show convergence. So we've kind of abstracted away the hard part by using prior methods that work.
Okay, I see. Okay, and one more question. So maybe page 15, I think. Page 15. So I was surprised to see this bound, because earlier work on a Riemannian setting, there was a geometric quantity like C. So why this bound does not have that quantity?
It doesn't have that quantity because in proximal point, you don't linearize the function. And so if you look at this, so if you do gradient descent, this inequality will always come up, right? If you do proximal point, it doesn't come up in the same way. And so you don't pay that error.
I see. Got it. That's why your bound is very simple, and like Euclidean bounds. Nice work. Okay, good. Thank you.
Okay, thank you for the great talk. So I'm curious, so this question is related to Akiko's questions just before. I'm curious whether the curvature plays a role in your analysis. I would assume that when the manifold is very flat, then it's a lot easier to do the optimization, and when it's kind of very curved, it's harder. So does it play a role in your analysis in the bounds or somehow?
Yeah, of course, because
that's it. I would think that Akiko, so I was asking a question about the bound. I would assume that the curvature somehow would appear somewhere in the bound, actually.
Yeah. So so this is the really nice thing about our online optimistic algorithm. There's no there's no geometric dependence in the regret, but the regret is not the complexity, right? The grid is just what the learner pays in this environment. However, in order to implement these steps here, right? Solve this and to solve this, you have to solve an optimization problem. And this one has these complexities here, right? So if you solve it with PRGD, then the complexity, if this becomes 1 because you choose 1 over eta step size, is zeta squared. So the complexity is like, so you have a linearly convergent algorithm, but it has a factor that depends on the geometry.
So this is theta here, you mean? This like zeta here
zeta.
depends on the complexity. Okay, okay. Okay, thank you.
None, then let's end our session here. Thank you very much.